Modern cloud architectures don't run on a single server. They exist as an interconnected web of thousands of microservice nodes. When specific nodes turn red and vanish, the network must instantly calculate a new path to keep data moving. This constant volatility means that even if every individual component is high quality, the sheer number of moving parts makes localized infrastructure failure a daily reality. Traditional quality assurance is designed to validate logic, asking, does the code work under expected conditions? But in a distributed environment, reliability engineering has to shift focus toward the aftermath of a break, analyzing how the system behaves when its dependencies disappear. This approach draws from chaos theory, the study of dynamical systems that are highly sensitive to initial conditions. In a software network, a single delayed packet or a minor API timeout can ripple through the architecture like a butterfly effect. Statistically, in a system of this complexity, the probability of every component functioning perfectly at the same time is nearly zero. The operational stakes are highest in sectors like global finance. When a bank processes tens of thousands of transactions per second, an unhandled node failure doesn't just slow down a website, it freezes instant payments and locks millions of customers out of their accounts. Relying on system stability without proactively engineering for these moments leaves the entire journey to chance. Within these high-stakes environments, hope is not a technical strategy. Standard unit and integration testing rely on linear assumptions. They validate the code based on how a developer expects the environment to behave, creating a sanitized model that rarely accounts for the unknown unknowns of the cloud. Isolated staging environments lack the physical scale to replicate the nonlinear realities of live production. They cannot simulate the exact latency of a global network or the replica drift that occurs when data across multiple regions falls out of sync. This leads to unpredictable blast radii. Without strictly bounded dependencies, a minor error in a non-critical service, like a recommendation engine, can consume all available connections and cascade until it brings down the core transaction database. Production also introduces variables that staging misses, such as the unique behavior of external messaging queues like Kafka or DNS rerouting under heavy stress. These components often react with unpredictable timing that a standard test environment simply cannot reproduce. Because traditional QA tests an idealized version of the architecture, it cannot guarantee resilience. The true state of the system remains unverified until it faces an actual failure in the live environment. For decades, engineers relied on legacy on-premise hardware that was hardened and highly predictable. Modern microservice deployments, however, function as a fluid and constantly evolving web of software-defined dependencies. Moving to the cloud shifts the burden of uptime from hardware guarantees to the resilience of the software itself. There is no longer a physical failsafe that software doesn't have to account for. A common engineering trap occurs when a new update passes every staging test but triggers a total outage the moment it hits live load. The live environment's traffic volume exposes a race condition or a communication error that was invisible in the low-volume test cluster. These failures are often caused by specific cloud-native bottlenecks, a circuit breaker that doesn't trip fast enough, a cache miss-storm that overwhelms a backend, or a database failover that takes longer than the application's timeout window. To address this, teams initially turned to manual game days. Engineers would manually run scripts to inject faults, like shutting down a server or dropping network packets, to observe the system's reaction. But manual testing is slow and requires high levels of human coordination. A single script can only test a narrow set of variables, making it an unreliable way to validate a system that changes every time a new piece of code is merged. As the number of services grows, manual oversight becomes a bottleneck. To match the speed of modern deployment, the validation of system resilience must be fully automated. A case study from a major bank illustrates why these automated tests are necessary. The goal was to validate an active-active OpenShift cluster setup, a design specifically intended to ensure high availability. In this configuration, an application gateway sits at the top, splitting traffic between two identical clusters. The design assumes that if cluster A fails, the gateway will detect the outage and instantly shift 100% of the traffic to cluster B. To verify this assumption, the site reliability team ran a production experiment, taking the primary cluster offline during active user traffic. The experiment revealed a critical failure in the gateway's logic. Though cluster A was dead, the gateway failed to detect the outage and continued routing user requests into the broken backend. The diagnosis revealed a configuration error in the telemetry. The health check timeout, the setting that tells the gateway when a cluster is dead, was set too high, leaving the gateway functionally blind. This misconfiguration created an operational blind spot that lasted for 50 seconds. During that brief window, every user session routed to cluster A was abruptly terminated, resulting in thousands of failed transactions. The test also exposed a flaw in the application code itself. It lacked the necessary reconnection logic to salvage the drop sessions, meaning the client-side app couldn't recover even if the gateway eventually rerouted the traffic. On paper, the system had redundant infrastructure, but because the health checks and retry logic weren't tuned correctly, the architecture failed to provide the high availability it was designed for. Redundancy is only theoretical until it is validated under the exact failure conditions it was built to survive. To catch these configuration errors before they cause a real outage, organizations must build a dedicated platform that automates the injection of failure. This platform uses a declarative interface. Instead of writing custom code for every test, an engineer selects a target service, defines load parameters, and chooses a failure scenario. The execution engine first runs the scenario in a staging cluster, ensuring the test is configured correctly and won't cause unexpected damage to the live environment. Integrated observability is the next pillar. The platform automatically pulls in system metrics, like latency and error rates, to correlate the injected failure with the drop in performance. Before reaching production, the test enters a governance phase. This gate requires strict human approval and defines a blast radius, ensuring the experiment is contained within a specific region. Once authorized, the platform injects the validated failure directly into the live production cluster, testing the architecture against real-world traffic and hardware. To maintain safety, the platform relies on an automated rollback trigger. If the experiment causes performance metrics to spike beyond a safe threshold, the engine instantly halts the test and reverts the cluster to its healthy state. This rollback provides the engineering team with a complete record of the system's exact breaking point without requiring a manual recovery or causing a lasting outage for the customer. The findings from these rollbacks are documented as new hypotheses, creating a continuous loop where the architecture is hardened against the very failures it just experienced. By combining this declarative interface with automated safety gates, the platform becomes a self-service capability. Individual developers can now safely schedule and run their own resilience tests on their specific services, turning a complex manual task into a routine part of the development lifecycle. While the back-end mechanics are critical, the ultimate test of resilience engineering is how a partial failure affects the person using the application. Consider the difference between these two screens. On the left is silent degradation, where a back-end failure leaves the app frozen on a loading spinner. The user is left in an unresponsive state, unsure if their transaction was processed or if their account is even accessible. For a user, this lack of clarity destroys trust far faster than an outright failure. An unresponsive interface suggests the system is out of control, while an explicit message provides immediate certainty. This forces a shift in design. Degraded modes, such as a read-only state that lets users see their balance even when they can't make transfers, must be treated as primary user journeys that are built and tested with the same rigor as the core product. True resilience is not about maintaining 100% uptime in a complex system. It is about ensuring that when the inevitable break occurs, the system's degradation is entirely predictable and clearly communicated to the user. Implementing an automated chaos framework does more than just fix bugs. It fundamentally reorients the engineering culture. Routine, controlled exposure to failure trains engineers to remain calm and decisive. They learn to identify the specific signals of an outage and communicate clearly under the pressure of a real incident. This proactive mindset shifts the development timeline. Engineers begin designing for failure scenarios before a single line of code is merged, rather than waiting for an alert to fire in the middle of the night. It moves the organization away from a reactive model of remediation and toward a proactive model of continuous validation. As distributed systems grow beyond the ability of any single human to monitor, relying on manual oversight is no longer a viable option. Chaos in complex systems is a certainty, but by adopting automated, observable frameworks, we can choose exactly how our systems will fail, ensuring that even in the middle of a break, our behavior remains predictable.